Earth, from Wikipedia, the free encyclopedia, at en.wikipedia.org. The text of this recording is current as of April 2021. The page contains the following sections. 1. Etymology. 2. Chronology, containing formation, geological history, origin of life and evolution, and future. 3. Physical characteristics, containing shape, chemical composition, internal structure, heat, tectonic plates, surface, gravitational field, and magnetic field. 4. Orbit and rotation, containing rotation, orbit, and axial tilt and seasons. 5. Earth-Moon system, containing moon and asteroids and artificial satellites. 6. Hydrosphere. 7. Atmosphere, containing weather and climate and upper atmosphere. 8. Life on Earth. 9. Human geography, containing natural resources and land use. 10. Cultural and historical viewpoint. The page has an info box containing much information, and an image, the blue marble, the most widely used photograph of Earth, taken by the Apollo 17 mission in 1972. Earth is the third planet from the Sun, and the only astronomical object known to harbour life. About 29% of Earth's surface is land, consisting of continents and islands. The remaining 71% is covered with water, mostly by oceans, seas, gulfs, and other saltwater bodies, but also by lakes, rivers, and other freshwater, which together constitute the hydrosphere. Much of Earth's polar regions are covered in ice. Earth's outer layer is divided into several rigid tectonic plates that migrate across the surface over many millions of years. Earth's interior remains active, with a solid iron inner core, a liquid outer core that generates Earth's magnetic field, and a convecting mantle that drives plate tectonics. Earth's atmosphere consists mostly of nitrogen and oxygen. More solar energy is received by tropical regions than polar regions, and is redistributed by atmospheric and ocean circulation. Greenhouse gases also play an important role in regulating the surface temperature. A region's climate is not only determined by latitude, but also by elevation, and by proximity to moderating oceans, among other factors. Extreme weather, such as tropical cyclones and heat waves, occur in most areas and has a large impact on life. Earth's gravity interacts with other objects in space, especially the Sun and the Moon, which is Earth's only natural satellite. Earth orbits around the Sun in about 365.25 days. Earth's axis of rotation is tilted with respect to its orbital plane, producing seasons on Earth. The gravitational interaction between the Earth and the Moon causes tides, stabilizes Earth's orientation on its axis, and gradually slows its rotation. Earth is the densest planet of the solar system, and the largest and most massive of the 4 rocky planets. According to radiometric dating estimation and other evidence, Earth formed over 4.5 billion years ago. Within the first billion years of Earth's history, life appeared in the oceans and began to affect Earth's atmosphere and surface, leading to the proliferation of anaerobic and, later, aerobic organisms. Some geological evidence indicates that life may have arisen as early as 4.1 billion years ago. Since then, the combination of Earth's distance from the Sun, physical properties, and geological history have allowed life to evolve and thrive. In the history of life on Earth, biodiversity has gone through long periods of expansion, occasionally punctuated by mass extinctions. Over 99% of all species that ever lived on Earth are extinct. Almost 8 billion humans live on Earth and depend on its biosphere and natural resources for their survival. Humans increasingly impact Earth's surface, hydrology, atmospheric processes, and other life. Section 1. Etymology. The modern English word earth developed, via Middle English, from an Old English noun most often spelled jörðu. It has cognates in every Germanic language, and their ancestral root has been reconstructed as ertho. In its earliest attestation, the word jörðu was already being used to translate the many senses of Latin terra and Greek the ground, its soil, dry land, the human world, the surface of the world, including the sea, and the globe itself. As with Roman terra or tullus and Greek Gaia, Earth may have been a personified goddess in Germanic paganism. Late Norse mythology included Jörð, a giantess often given as the mother of Thor. Historically, Earth has been written in lower case. From early Middle English, its definite sense as the globe was expressed as the Earth. By early modern English, many nouns were capitalized, and the Earth was also written as the Earth with a capital E, particularly when referenced along with other heavenly bodies. More recently, the name is sometimes given as Earth, with a capital E, by analogy with the names of the other planets, though Earth, lowercase e, and forms with the remain common. House styles now vary. Oxford spelling recognises the lowercase form as the most common, with the capitalised form an acceptable variant. Another convention capitalises Earth when appearing as a name, for example, Earth's atmosphere, but writes it in lowercase when preceded by the, for example, the atmosphere of the Earth. It almost always appears in lowercase in colloquial expressions such as, "What on earth are you doing?" Occasionally, the name Terra is used in scientific writing and especially in science fiction to distinguish humanity's inhabited planet from others, while in poetry, Tellus has been used to denote personification of the Earth. The Greek poetic name Gaia is rare, though the alternative spelling Gaia has become common due to the Gaia hypothesis, in which case its pronunciation is Gaia, rather than the more classical Gaia. There are a number of adjectives for the planet Earth. From Earth itself comes earthly, from the Latin terra comes terran, terrestrial, and, via French, terrain, and from the Latin tellus comes tellurian and telluric. Section 2. Chronology. Main article, History of Earth. Section 2.1. Formation. There's an image, artist's impression of the early solar system's planetary disk. The oldest material found in the solar system is dated to 4.5682 billion years ago. By 4.54 plus or minus 0.04 billion years ago, the primordial Earth had formed. The bodies in the solar system formed and evolved with the Sun. In theory, a solar nebula partitions a volume out of a molecular cloud by gravitational collapse, which begins to spin and flatten into a circumstellar disk, and then the planets grow out of that disk with the Sun. A nebula contains gas, ice grains, and dust, including primordial nuclides. According to nebular theory, planetesimals formed by accretion, with the primordial Earth being estimated as likely taking anywhere from 70 to 100 million years to form. Estimates of the age of the Moon range from 4.5 billion years ago to significantly younger. A leading hypothesis is that it was formed by accretion from material loosed from Earth after a Mars-sized object with about 10% of Earth's mass, named Theia, collided with Earth. It hit Earth with a glancing blow, and some of its mass merged with Earth. Between approximately 4.1 and 3.8 billion years ago, numerous asteroid impacts during the late heavy bombardment caused significant changes to the greater surface environment of the Moon and, by inference, to that of Earth. Section 2.2. Geological History. Main article, Geological History of Earth. There's an image, Carboniferous rocks that were folded, uplifted and eroded during the orogeny that completed the formation of the Pangaea supercontinent before deposition of the overlying Triassic strata, in the Algarve Basin, which marked the start of its breakup. Earth's atmosphere and oceans were formed by volcanic activity and outgassing. Water vapour from these sources condensed into the oceans, augmented by water and ice from asteroids, protoplanets and comets. Sufficient water to fill the oceans may have always been on Earth since the beginning of the planet's formation. In this model, atmospheric greenhouse gases kept the oceans from freezing, while the newly forming Sun had only 70% of its current luminosity. By 3.5 billion years ago, Earth's magnetic field was established, which helped prevent the atmosphere from being stripped away by the solar wind. As the molten outer layer of Earth cooled, it formed the first solid crust, which is thought to have been mafic in composition. The first continental crust, which was more felsic in composition, formed by the partial melting of this mafic crust. The presence of grains of the mineral zircon of Hadean age in Eoarchean sedimentary rocks suggests that at least some felsic crust existed as early as 4.4 billion years ago, only 140 million years after Earth's formation. There are two main models of how this initial small volume of continental crust evolved to reach its current abundance. One, a relatively steady growth up to the present day, which is supported by the radiometric dating of continental crust globally, and two, an initial rapid growth in the volume of continental crust during the Archean, forming the bulk of the continental crust that now exists, which is supported by isotopic evidence from hafnium in zircons and neodymium in sedimentary rocks. The two models, and the data that support them, can be reconciled by large-scale recycling of the continental crust, particularly during the early stages of Earth's history. New continental crust forms as a result of plate tectonics, a process ultimately driven by the continuous loss of heat from Earth's interior. Over the period of hundreds of millions of years, tectonic forces have caused areas of continental crust to group together to form supercontinents that have subsequently broken apart. At approximately 750 million years ago, one of the earliest known supercontinents, Rodinia, began to break apart. The continents later recombined to form Pannotia at 600 to 540 million years ago, then finally Pangaea, which also began to break apart at 180 million years ago. The most recent pattern of ice ages began about 40 million years ago, and then intensified during the Pleistocene about 3 million years ago. High and middle latitude regions have since undergone repeated cycles of glaciation and thaw, repeating about every 21,000, 41,000, and 100,000 years. The last glacial period, colloquially called the Last Ice Age, covered large parts of the continents up to the middle latitudes in ice and ended about 11,700 years ago. Section 2.3 Origin of Life and Evolution. Main articles: Origin of Life and Evolutionary History of Life. There's an accompanying diagram: Life Timeline. Chemical reactions led to the first self-replicating molecules about 4 billion years ago. A half billion years later, the last common ancestor of all current life arose. The evolution of photosynthesis allowed the sun's energy to be harvested directly by life forms. The resultant molecular oxygen, O2, accumulated in the atmosphere, and due to the interaction with ultraviolet solar radiation, formed a protective ozone layer, O3, in the upper atmosphere. The incorporation of smaller cells within larger ones resulted in the development of complex cells called eukaryotes. True multicellular organisms formed as cells within colonies became increasingly specialized. Aided by the absorption of harmful ultraviolet radiation by the ozone layer, life colonized Earth's surface. Among the earliest fossil evidence for life is microbial mat fossils found in 3.48 billion-year-old sandstone in Western Australia, biogenic graphite found in 3.7 billion-year-old metasedimentary rocks in Western Greenland, and remains of biotic material found in 4.1 billion-year-old rocks in Western Australia. The earliest direct evidence of life on Earth is contained in 3.45 billion-year-old Australian rocks showing fossils of microorganisms. During the Neoproterozoic, 1,000 to 541 million years ago, much of Earth might have been covered in ice. This hypothesis has been termed snowball Earth, and is of particular interest because it preceded the Cambrian explosion, when multicellular life forms significantly increased in complexity. Following the Cambrian explosion, 535 million years ago, there have been at least 5 major mass extinctions and many minor ones. Apart from the proposed current Holocene extinction event, the most recent was 66 million years ago, when an asteroid impact triggered the extinction of the non-avian dinosaurs and other large reptiles, but largely spared small animals such as insects, mammals, lizards, and birds. Mammalian life has diversified over the past 66 million years, and several million years ago, an African ape gained the ability to stand upright. This facilitated tool use and encouraged communication that provided the nutrition and stimulation needed for a larger brain, which led to the evolution of humans. The development of agriculture, and then civilization, led to humans having an influence on Earth and the nature and quantity of other life forms that continues to this day. Over 99% of all species that have ever lived on Earth are extinct. Section 2.4 Future. Main article, Future of Earth. See also, Global Catastrophic Risk. Because carbon dioxide, CO2, has a long lifespan in the atmosphere, moderate human CO2 emissions may postpone the next glacial inception by 100,000 years. Earth's expected long-term future is tied to that of the Sun. Over the next 1.1 billion years, solar luminosity will increase by 10%, and over the next 3.5 billion years by 40%. Earth's increasing surface temperature will accelerate the inorganic carbon cycle, reducing CO2 concentration to levels lethally low for plants, 10 parts per million for C4 photosynthesis, in approximately 100 to 900 million years. The lack of vegetation will result in the loss of oxygen in the atmosphere, making animal life impossible. Due to the increased luminosity, Earth's mean temperature may reach 100 degrees Celsius, 212 degrees Fahrenheit, in 1.5 billion years, and all ocean water will evaporate and be lost to space within an estimated 1.6 to 3 billion years. Even if the Sun were stable, a fraction of the water in the modern oceans will descend to the mantle due to reduced steam venting from mid-ocean ridges. The Sun will evolve to become a red giant in about 5 billion years. Models predict that the Sun will expand to roughly 1 astronomical unit, 150 million kilometers or 93 million miles, about 250 times its present radius. Earth's fate is less clear. As a red giant, the Sun will lose roughly 30% of its mass, so, without tidal effects, Earth will move to an orbit 1.7 astronomical units, 250 million kilometers or 160 million miles, from the Sun, when the star reaches its maximum radius. Section 3. Physical Characteristics. Section 3.1. Shape. Main articles, Figure of the Earth, Earth radius, and Earth's circumference. There is an image, the summit of Chimborazo, the point on Earth's surface that is farthest from Earth's centre. The shape of Earth is nearly spherical. There is a small flattening at the poles and bulging around the equator due to Earth's rotation, so that a better approximation of Earth's shape is an oblate spheroid whose equatorial diameter is 43 kilometers, 27 miles, larger than the pole-to-pole diameter. The point on the surface farthest from Earth's centre of mass is the summit of the equatorial Chimborazo volcano in Ecuador, 6,384.4 kilometers or 3,967.1 miles. The average diameter of the reference spheroid is 12,742 kilometers, 7,918 miles. Local topography deviates from this idealized spheroid, although on a global scale, these deviations are small compared to Earth's radius. The maximum deviation of only 0.17% is at the Mariana Trench, 10,925 meters or 35,843 feet below local sea level, whereas Mount Everest, 8,848 meters or 29,029 feet above local sea level, represents a deviation of 0.14%. In geodesy, the exact shape that Earth's oceans would adopt in the absence of land and perturbations such as tides and winds is called the geoid. More precisely, the geoid is the surface of gravitational equipotential at mean sea level. Section 3.2. Chemical composition. See also Abundance of elements on Earth. There is a table chemical composition of the crust. Earth's mass is approximately 5.97 times 10 to the power of 24 kilograms. It is composed mostly of iron, 32.1%, oxygen, 30.1%, silicon, 15.1%, magnesium, 13.9%, sulfur, 2.9%, nickel, 1.8%, calcium, 1.5%, and aluminium, 1.4%, with the remaining 1.2% consisting of trace amounts of other elements. Due to mass segregation, the core region is estimated to be primarily composed of iron, 88.8%, with smaller amounts of nickel, 5.8%, sulfur, 4.5%, and less than 1% trace elements. The most common rock constituents of the crust are nearly all oxides. Chlorine, sulfur, and fluorine are the important exceptions to this, and their total amount in any rock is usually much less than 1%. Over 99% of the crust is composed of 11 oxides, principally silica, alumina, iron oxides, lime, magnesia, potash, and soda. Section 3.3 Internal Structure. Main article, Structure of the Earth. There is a diagram and table, Geologic Layers of Earth. Earth cutaway from core to exosphere, not to scale. Earth's interior, like that of the other terrestrial planets, is divided into layers by their chemical or physical, rheological, properties. The outer layer is a chemically distinct silicate solid crust, which is underlain by a highly viscous solid mantle. The crust is separated from the mantle by the Mohorovicic discontinuity. The thickness of the crust varies from about 6 kilometers, 3.7 miles, under the oceans, to 30 to 50 kilometers, 19 to 31 miles, for the continents. The crust and the cold, rigid top of the upper mantle are collectively known as the lithosphere, which is divided into independently moving tectonic plates. Beneath the lithosphere is the asthenosphere, a relatively low viscosity layer on which the lithosphere rides. Important changes in crystal structure within the mantle occur at 410 and 660 kilometers, 250 and 410 miles, below the surface, spanning a transition zone that separates the upper and lower mantle. Beneath the mantle, an extremely low viscosity liquid outer core lies above a solid inner core. Earth's inner core may be rotating at a slightly higher angular velocity than the remainder of the planet, advancing by 0.1 to 0.5 degrees per year, although both somewhat higher and much lower rates have also been proposed. The radius of the inner core is about 1/5 of that of Earth. Density increases with depth, as described in the table. Section 3.4 Heat. Main article, Earth's internal heat budget. The major heat-producing isotopes within Earth are potassium-40, uranium-238, and thorium-232. At the centre, the temperature may be up to 6,000 degrees Celsius, 10,830 degrees Fahrenheit, and the pressure could reach 360 gigapascals, 52 million pounds per square inch. Because much of the heat is provided by radioactive decay, scientists postulate that early in Earth's history, before isotopes with short half-lives were depleted, Earth's heat production was much higher. At approximately 3 billion years, twice the present-day heat would have been produced, increasing the rate of mantle convection and plate tectonics, and allowing the production of uncommon igneous rocks such as komatiites that are rarely formed today. There is a table, present-day major heat-producing isotopes. The mean heat loss from Earth is 87 milliwatts per square meter, for a global heat loss of 4.42 times 10 to the power of 13 watts. A portion A portion of the core's thermal energy is transported toward the crust by mantle plumes, a form of convection consisting of upwellings of higher temperature rock. These plumes can produce hotspots and flood basalts. More of the heat in Earth is lost through plate tectonics, by mantle upswelling associated with mid-ocean ridges. The final major mode of heat loss is through conduction through the lithosphere, the majority of which occurs under the oceans because the crust there is much thinner than that of the continents. Section 3.5 Tectonic Plates. Main article, Plate Tectonics. There's an image and a table, Earth's major plates. Earth's mechanically rigid outer layer, the lithosphere, is divided into tectonic plates. These plates are rigid segments that move relative to each other at one of three boundaries types. At convergent boundaries, two plates come together. At divergent boundaries, two plates are pulled apart. And at transform boundaries, two plates slide past one another laterally. Along these plate boundaries, earthquakes, volcanic activity, mountain building, and oceanic trench formation can occur. The tectonic plates ride on top of the asthenosphere, the solid but less viscous part of the upper mantle that can flow and move along with the plates. As the tectonic plates migrate, oceanic crust is subducted under the leading edges of the plates at convergent boundaries. At the same time, the upwelling of mantle material at divergent boundaries creates mid-ocean ridges. The combination of these processes recycles the oceanic crust back into the mantle. Due to this recycling, most of the ocean floor is less than 100 million years old. The oldest oceanic crust is located in the Western Pacific and is estimated to be 200 million years old. By comparison, the oldest dated continental crust is 4,030 million years old, although zircons have been found preserved as clasts within Eoarchean sedimentary rocks that give ages up to 4,400 million years, indicating that at least some continental crust existed at that time. The seven major plates are the Pacific, North American, Eurasian, African, Antarctic, Indo-Australian, and South American. Other notable plates include the Arabian Plate, the Caribbean Plate, the Nazca Plate off the west coast of South America, and the Scotia Plate in the southern Atlantic Ocean. The Australian Plate fused with the Indian Plate between 50 and 55 million years ago. The fastest moving plates are the Oceanic Plates, with the Cocos Plate advancing at a rate of 75 millimeters per year, 3 inches per year, and the Pacific Plate moving 52 to 69 millimeters per year, 2.0 to 2.7 inches per year. At the other extreme, the slowest moving plate is the South American Plate, progressing at a typical rate of 10.6 millimeters per year, 0.42 inches per year. Section 3.6 Surface. Main articles: Earth's crust, landform, and extreme points of Earth. See also planetary surface and geomorphology. There's an image. Current Earth without water, elevation greatly exaggerated. Click and enlarge to spin the 3D globe. The total surface area of Earth is about 510 million square kilometers, 197 million square miles. Of this, 70.8%, or 361.13 million square kilometers, 139.43 million square miles, is below sea level and covered by ocean water. Below the ocean's surface are much of the continental shelf, mountains, volcanoes, oceanic trenches, submarine canyons, oceanic plateaus, abyssal plains, and a globe-spanning mid-ocean ridge system. The remaining 29.2%, or 148.94 million square kilometers, 57.51 million square miles, not covered by water, has terrain that varies greatly from place to place and consists of mountains, deserts, plains, plateaus, and other landforms. The elevation of the land surface varies from the low point of negative 418 metres, negative 1,371 feet, at the Dead Sea, to a maximum altitude of 8,848 metres, 29,029 feet, at the top of Mount Everest. The mean height of land above sea level is about 797 metres, 2,615 feet. The continental crust consists of lower density material such as the igneous rocks granite and andesite. Less common is basalt, a denser volcanic rock that is the primary constituent of the ocean floors. Sedimentary rock is formed from the accumulation of sediment that becomes buried and compacted together. Nearly 75% of the continental surfaces are covered by sedimentary rocks, although they form about 5% of the crust. The third form of rock material found on Earth is metamorphic rock, which is created from the transformation of pre-existing rock types through high pressures, high temperatures, or both. The most abundant silicate minerals on Earth's surface include quartz, feldspars, amphibole, mica, pyroxene, and olivine. Common carbonate minerals include calcite, found in limestone, and dolomite. Erosion and tectonics, volcanic eruptions, flooding, weathering, glaciation, the growth of coral reefs, and meteorite impacts are among the processes that constantly reshape Earth's surface over geological time. The pedosphere is the outermost layer of Earth's continental surface and is composed of soil and subject to soil formation processes. The total arable land is 10.9% of the land surface, with 1.3% being permanent cropland. Close to 40% of Earth's land surface is used for agriculture, on an estimated 16.7 million square kilometres, 6.4 million square miles, of cropland, and 33.5 million square kilometres, 12.9 million square miles, of pasture land. Section 3.7. Gravitational Field. Main article, Gravity of Earth. There's an image, Earth's gravity measured by NASA's GRACE mission, showing deviations from the theoretical gravity. Red shows where gravity is stronger than the smooth standard value, and blue shows where it is weaker. The gravity of Earth is the acceleration that is imparted to objects due to the distribution of mass within Earth. Near Earth's surface, gravitational acceleration is approximately 9.8 meters per second, 32 feet per second. Local differences in topography, geology, and deeper tectonic structure cause local and broad regional differences in Earth's gravitational field, known as gravity anomalies. Section 3.8. Magnetic Field. Main article, Earth's magnetic field. The main part of Earth's magnetic field is generated in the core, the site of a dynamo process that converts the kinetic energy of thermally and compositionally driven convection into electrical and magnetic field energy. The field extends outwards from the core, through the mantle, and up to Earth's surface, where it is, approximately, a dipole. The poles of the dipole are located close to Earth's geographic poles. At the equator of the magnetic field strength at the surface is 3.05 times 10 to the minus 5 teslas, with a magnetic dipole moment of 7.79 times 10 to the power of 22 ampere square meters at epoch 2000, decreasing nearly 6% per century. The convection movements in the core are chaotic. The magnetic poles drift and periodically change alignment. This causes secular variation of the main field and field reversals at irregular intervals averaging a few times every million years. The most recent reversal occurred approximately 700,000 years ago. 3.8.1. Magnetosphere. Main article, Magnetosphere. There's an image, schematic of Earth's magnetosphere. The solar wind flows from left to right. The extent of Earth's magnetic field in space defines the magnetosphere. Ions and electrons of the solar wind are deflected by the magnetosphere. Solar wind pressure compresses the day side of the magnetosphere to about 10 Earth radii and extends the night side magnetosphere into a long tail. Because the velocity of the solar wind is greater than the speed at which waves propagate through the solar wind, a supersonic bow shock precedes the day side magnetosphere within the solar wind. Charged particles are contained within the magnetosphere. The plasmasphere is defined by low-energy particles that essentially follow magnetic field lines as Earth rotates. The ring current is defined by medium-energy particles that drift relative to the geomagnetic field, but with paths that are still dominated by the magnetic field. And the Van Allen radiation belts are formed by high-energy particles whose motion is essentially random but contained in the magnetosphere. During magnetic storms and substorms, charged particles can be deflected from the outer magnetosphere, and especially the magnetotail, directed along field lines into Earth's ionosphere, where atmospheric atoms can be excited and ionized, causing the aurora. Section 4. Orbit and Rotation. Section 4.1. Rotation. Main article, Earth's rotation. There's an image, Earth's rotation, imaged by DSCOVR EPIC on the 29th of May 2016, a few weeks before a solstice. Earth's rotation period relative to the Sun, its mean solar day, is 86,400 seconds of mean solar time, 86,400.0025 SI seconds. Because Earth's solar day is now slightly longer than it was during the 19th century due to tidal deceleration, each day varies between 0 and 2 milliseconds longer than the mean solar day. Earth's rotation period relative to the fixed stars, called its stellar day by the International Earth Rotation and Reference System Service, IERS, is 86,164.0989 seconds of mean solar time, UT1, or 23 hours, 56 minutes, and 4.0989 seconds. Earth's rotation period relative to the precessing or moving mean March equinox, when the Sun is at 90 degrees on the equator, is 86,164.0905 seconds of mean solar time, UT1, 23 hours, 56 minutes, 4.0905 seconds. Thus, the sidereal day is shorter than the stellar day by about 8.4 milliseconds. Apart from meteors within the atmosphere and low-orbiting satellites, the main apparent motion of celestial bodies in Earth's sky is to the west at a rate of 15 degrees per hour, or 15 minutes per minute. For bodies near the celestial equator, this is equivalent to an apparent diameter of the Sun or the Moon every 2 minutes. From Earth's surface, the apparent sizes of the Sun and Moon are approximately the same. Section 4.2. Orbit. Main article, Earth's orbit. There's an image, the pale blue dot photo, taken in 1990 by the Voyager 1 spacecraft, showing Earth, centre right, from nearly 6.0 billion kilometres, 3.7 billion miles, away, about 5.6 hours at light speed. Earth orbits the Sun at an average distance of about 150 million kilometres, 93 million miles, every 365.2564 mean solar days, or 1 sidereal year. This gives an apparent movement of the Sun eastward with respect to the stars at a rate of about 1 degree per day, which is 1 apparent Sun or Moon diameter every 12 hours. Due to this motion, on average it takes 24 hours, a solar day, for Earth to complete a full rotation about its axis so that the Sun returns to the meridian. The orbital speed of Earth averages about 29.78 kilometers per second, 107,200 kilometers per hour or 66,600 miles per hour, which is fast enough to travel a distance equal to Earth's diameter, about 12,742 kilometers, 6,918 miles, in 7 minutes, and the distance to the Moon, 384,000 kilometers, 239,000 miles, in about 3.5 hours. The Moon and Earth orbit a common barycenter every 27.32 days relative to the background stars. When combined with the Earth-Moon system's common orbit around the Sun, the period of the synodic month, from new moon to new moon, is 29.53 days. Viewed from the celestial North Pole, the motion of Earth, the Moon, and their axial rotations are all counterclockwise. Viewed from a vantage point above the North Poles of both the Sun and Earth, Earth orbits in a counterclockwise direction about the Sun. The orbital and axial planes are not precisely aligned. Earth's axis is tilted some 23.44 degrees from the perpendicular to the Earth-Sun plane, the ecliptic, and the Earth-Moon plane is tilted up to plus or minus 5.1 degrees against the Earth-Sun plane. Without this tilt, there would be an eclipse every 2 weeks, alternating between lunar eclipses and solar eclipses.
The Hill sphere, or the sphere of gravitational influence of Earth, is about 1.5 million kilometers, 930,000 miles, in radius. This is the maximum distance at which Earth's gravitational influence is stronger than the more distant Sun and planets. Objects must orbit Earth within this radius, or they can become unbound by the gravitational perturbation of the Sun. Earth, along with the Solar System, is situated in the Milky Way and orbits about 28,000 light-years from its centre. It is about 20 light-years above the galactic plane in the Orion Arm. Section 4.3. Axial Tilt and Seasons. Main article, Axial Tilt, Earth. There's an image, Earth's axial tilt, or obliquity, and its relation to the rotation axis and plane of orbit. The axial tilt of Earth is approximately 23.439281 degrees with the axis of its orbit plane, always pointing towards the celestial poles. Due to Earth's axial tilt, the amount of sunlight reaching any given point on the surface varies over the course of the year. This causes the seasonal change in climate, with summer in the northern hemisphere occurring when the Tropic of Cancer is facing the Sun, and in the southern hemisphere when the Tropic of Capricorn faces the Sun. In each instance, winter occurs simultaneously in the opposite hemisphere. During the summer, the day lasts longer and the Sun climbs higher in the sky. In winter, the climate becomes cooler and the days shorter. Above the Arctic Circle and below the Antarctic Circle, there is no daylight at all for part of the year, causing a polar night, and this night extends for several months at the poles themselves. These same latitudes also experience a midnight sun, where the sun remains visible all day. By astronomical convention, the 4 seasons can be determined by the solstices, the points in the orbit of maximum axial tilt toward or away from the Sun, and the equinoxes, when Earth's rotational axis is aligned with its orbital axis. In the northern hemisphere, winter solstice currently occurs around the 21st of December, summer solstice is near the 21st of June, spring equinox is around the 20th of March, and the autumnal equinox is about 22nd or 23rd of September. In the southern hemisphere, the situation is reversed, with the summer and winter solstices exchanged, and the spring and autumnal equinox dates swapped. The angle of Earth's axial tilt is relatively stable over long periods of time. Its axial tilt does undergo nutation, a slight, irregular motion with a main period of 18.6 years. The orientation, rather than the angle, of Earth's axis also changes over time, precessing around in a complete circle over each 25,800-year cycle. This precession is the reason for the difference between a sidereal year and a tropical year. Both of these motions are caused by the varying attraction of the Sun and the Moon on Earth's equatorial bulge. The poles also migrate a few meters across Earth's surface. This polar motion has multiple cyclical components, which collectively are termed quasi-periodic motion. In addition to an annual component to this motion, there is a 14-month cycle called the Chandler wobble. Earth's rotational velocity also varies in a phenomenon known as length of day variation. In modern times, Earth's perihelion occurs around the 3rd of January, and its aphelion around the 4th of July. These dates change over time due to precession and other orbital factors, which follow cyclical patterns known as Milankovitch cycles. The changing Earth-Sun distance causes an increase of about 6.8% in solar energy reaching Earth at perihelion relative to aphelion. Because the southern hemisphere is tilted towards the Sun at about the same time that Earth reaches the closest approach to the Sun, the southern hemisphere receives slightly more energy from the Sun than does the northern over the course of a year. This effect is much less significant than the total energy change due to the axial tilt, and most of the excess energy is absorbed by the higher proportion of water in the southern hemisphere. Section 5. Earth-Moon System. Main articles, Orbit of the Moon and Satellite System Astronomy. See also Claimed Moons of Earth, Quasi-Satellite, Co-Orbital Moon, Co-Orbital Configuration and Temporary Satellite. Section 5.1. Moon. Main articles, Moon and Lunar Theory. There is an image of the Moon and an accompanying table of characteristics of the Moon. The Moon is a relatively large, terrestrial, planet-like natural satellite, with a diameter of about 1/4 of Earth's. It is the largest moon in the solar system relative to the size of its planet, although Charon is larger relative to the dwarf planet Pluto. The natural satellites of other planets are also referred to as moons after Earth's. The most widely accepted theory of the Moon's origin, the giant impact hypothesis, states that it formed from the collision of a Mars-sized protoplanet called Theia with the early Earth. This hypothesis explains, among other things, the Moon's relative lack of iron and volatile elements, and the fact that its composition is nearly identical to that of Earth's crust. The gravitational attraction between Earth and the Moon causes tides on Earth. The same effect on the Moon has led to its tidal locking. Its rotational period is the same as the time it takes to orbit Earth. As a result, it always presents the same face to the planet. As the Moon orbits Earth, different parts of its face are illuminated by the Sun, leading to the lunar phases. Due to their tidal interaction, the Moon recedes from Earth at the rate of approximately 38 millimeters per year, 1.5 inches per year. Over millions of years, these tiny modifications, and the lengthening of Earth's day by about 23 microseconds per year, add up to significant changes. During the Ediacaran period, for example, approximately 620 million years ago, there were 400 plus or minus 7 days in a year, with each day lasting 21.9 plus or minus 0.4 hours. The Moon may have dramatically affected the development of life by moderating the planet's climate. Paleontological evidence and computer simulations show that Earth's axial tilt is stabilized by tidal interactions with the Moon. Some theorists think that without this stabilization against the torques applied by the Sun and planets to Earth's equatorial bulge, the rotational axis might be chaotically unstable, exhibiting large changes over millions of years, as is the case for Mars, though this is disputed. Viewed from Earth, the Moon is just far enough away to have almost the same apparent size disk as the Sun. The angular size, or solid angle, of these two bodies match because, although the Sun's diameter is about 400 times as large as the Moon's, it is also 400 times more distant. This allows total and annular solar eclipses to occur on Earth. Section 5.2 Asteroids and Artificial Satellites. Main article, Near-Earth Object. There's an image, Tracy Caldwell Dyson viewing Earth from the ISS Cupola, 2010. Earth's co-orbital asteroids population consists of quasi-satellites, objects with a horseshoe object, and Trojans. There are at least 5 quasi-satellites, including 469219 Kamo'oa Lewa. A Trojan asteroid companion, 2010 TK7, is librating around the leading Lagrange triangular point, L4, in Earth's orbit around the Sun. The tiny near-Earth asteroid 2006 RH120 makes close approaches to the Earth-Moon system roughly every 20 years. During these approaches, it can orbit Earth for brief periods of time. As of April 2020, there are 2,666 operational human-made satellites orbiting Earth. There are also inoperative satellites, including Vanguard 1, the oldest satellite currently in orbit, and over 16,000 pieces of tracked space debris. Earth's largest artificial satellite is the International Space Station.
Section 6. Hydrosphere. Main article, Hydrosphere. There's an image. Water is transported to various parts of the hydrosphere via the water cycle. The abundance of water on Earth's surface is a unique feature that distinguishes the blue planet from other planets in the solar system. Earth's hydrosphere consists chiefly of the oceans, but technically includes all water surfaces in the world, including inland seas, lakes, rivers, and underground waters down to a depth of 2,000 meters, 6,600 feet. The mass of the oceans is approximately 1.35 times 10 to the power of 18 metric tons, or about 1/4400th of Earth's total mass. The oceans cover an area of 361.8 million square kilometers, 139.7 million square miles, with a mean depth of 3,682 metres, 12,080 feet, resulting in an estimated volume of 1.332 billion cubic kilometres, 320 million cubic miles. If all of Earth's crustal surface were at the same elevation as a smooth sphere, the depth of the resulting world ocean would be 2.7 to 2.8 kilometres, 1.68 to 1.74 miles. About 97.5% of the water is saline. The remaining 2.5% is fresh water. Most fresh water, about 68.7%, is present as ice in ice caps and glaciers. In Earth's coldest regions, snow survives over the summer and changes into ice. This accumulated snow and ice eventually forms into glaciers, bodies of ice that flow under the influence of their own gravity. Alpine glaciers form in mountainous areas, whereas vast ice sheets form over land in polar regions. The flow of glaciers erodes the surface, changing it dramatically, with the formation of U-shaped valleys and other landforms. Sea ice in the Arctic covers an area about as big as the United States, although it is quickly retreating as a consequence of climate change. The average salinity of Earth's oceans is about 35 grams of salt per kilogram of seawater, 3.5% salt. Most of this salt was released from volcanic activity or extracted from cool igneous rocks. The oceans are also a reservoir of dissolved atmospheric gases, which are essential for the survival of many aquatic life forms. Seawater has an important influence on the world's climate, with the oceans acting as a large heat reservoir. Shifts in the oceanic temperature distribution can cause significant weather shifts, such as the El Niño Southern Oscillation.
Section 7. Atmosphere. Main article, Atmosphere of Earth. There's an image, satellite image of Earth cloud cover using NASA's Moderate Resolution Imaging Spectroradiometer. The atmospheric pressure at Earth's sea level averages 101.325 kilopascals, 14.696 pounds per square inch, with a scale height of about 8.5 kilometres, 5.3 miles. A dry atmosphere is composed of 78.084% nitrogen, 20.946% oxygen, 0.934% argon, and trace amounts of carbon dioxide and other gaseous molecules. Water vapour content varies between 0.01% and 4%, but averages about 1%. The height of the troposphere varies with latitude, ranging between 8 kilometres, 5 miles, at the poles, to 17 kilometres, 11 miles, at the equator, with some variation resulting from weather and seasonal factors. Earth's biosphere has significantly altered its atmosphere. Oxygenic photosynthesis evolved 2.7 billion years ago, forming the primary nitrogen-oxygen atmosphere of today. This change enabled the proliferation of aerobic organisms and, indirectly, the formation of the ozone layer due to the subsequent conversion of atmospheric O2 into O3. The ozone layer blocks ultraviolet solar radiation, permitting life on land. Other atmospheric functions important to life include transporting water vapour, providing useful gases, causing small meteors to burn up before they strike the surface, and moderating temperature. This last phenomenon is known as the greenhouse effect. Trace molecules within the atmosphere serve to capture thermal energy emitted from the ground, thereby raising the average temperature. Water vapour, carbon dioxide, methane, nitrous oxide, and ozone are the primary greenhouse gases in the atmosphere. Without this heat retention effect, the average surface temperature would be minus 18 degrees Celsius, 0 degrees Fahrenheit, in contrast to the current 15 degrees Celsius, 59 degrees Fahrenheit, and life on Earth would probably not exist in its current form. Section 7.1. Weather and Climate. Main articles, Weather and Climate. There are two images, Hurricane Felix seen from low Earth orbit, September 2007, and massive clouds above the Mojave Desert, February 2016. Earth's atmosphere has no definite boundary, slowly becoming thinner and fading into outer space. 3/4 of the atmosphere's mass is contained within the first 11 kilometers (6.8 miles) of the surface. This lowest layer is called the troposphere. Energy from the sun heats this layer and the surface below, causing expansion of the air. This lower density air then rises and is replaced by cooler, higher density air. The result is atmospheric circulation that drives the weather and climate through redistribution of thermal energy. The primary atmospheric circulation bands consist of the trade winds in the equatorial region below 30 degrees latitude and the westerlies in the mid-latitudes between 30 degrees and 60 degrees. Ocean currents are also important factors in determining climate, particularly the thermohaline circulation that distributes thermal energy from the equatorial oceans to the polar regions. The amount of solar energy reaching Earth's surface decreases with increasing latitude. At higher latitudes, the sunlight reaches the surface at lower angles, and it must pass through thicker columns of the atmosphere. As a result, the mean annual air temperature at sea level decreases by about 0.4 degrees Celsius (0.7 degrees Fahrenheit) per degree of latitude from the equator. Earth's surface can be subdivided into specific latitudinal belts of approximately homogeneous climate. Ranging from the equator to the polar regions, these are the tropical or equatorial, subtropical, temperate, and polar climates. Further factors that affect a location's climates are its proximity to oceans, the oceanic and atmospheric circulation, and topology. Places close to oceans typically have colder summers and warmer winters, due to the fact that oceans can store large amounts of heat. The wind transports the cold or the heat of the ocean to the land. Atmospheric circulation also plays an important role. San Francisco and Washington, D.C. are both coastal cities at about the same latitude. San Francisco's climate is significantly more moderate, as the prevailing wind direction is from sea to land. Finally, temperatures decrease with height, causing mountainous areas to be colder than low-lying areas. Water vapor generated through surface evaporation is transported by circulatory patterns in the atmosphere. When atmospheric conditions permit an uplift of warm, humid air, this water condenses and falls to the surface as precipitation. Most of the water is then transported to lower elevations by river systems, and usually returned to the oceans or deposited into lakes. This water cycle is a vital mechanism for supporting life on land, and is a primary factor in the erosion of surface features over geological periods. Precipitation patterns vary widely, ranging from several meters of water per year to less than a millimeter. Atmospheric circulation, topographic features, and temperature differences determine the average precipitation that falls in each region. The commonly used Köppen climate classification system has 5 broad groups: humid tropics, arid, humid middle latitudes, continental, and cold polar, which are further divided into more specific subtypes. The Köppen system rates regions based on observed temperature and precipitation. Surface air temperature can rise to around 55 degrees Celsius, 131 degrees Fahrenheit, in hot deserts, such as Death Valley, and can fall as low as minus 89 degrees Celsius, minus 128 degrees Fahrenheit, in Antarctica. Section 7.2. Upper Atmosphere. There's an image. This view from orbit shows the full moon partially obscured by Earth's atmosphere. Above the troposphere, the atmosphere is usually divided into the stratosphere, mesosphere, and thermosphere. Each layer has a different lapse rate, defining the rate of change in temperature with height. Beyond these, the exosphere thins out into the magnetosphere, where the geomagnetic fields interact with the solar wind. Within the stratosphere is the ozone layer, a component that partially shields the surface from ultraviolet light and thus is important for life on Earth. The Kármán line, defined as 100 kilometers above Earth's surface, is a working definition for the boundary between the atmosphere and outer space. Thermal energy causes some of the molecules at the outer edge of the atmosphere to increase their velocity to the point where they can escape from Earth's gravity. This causes a slow but steady loss of the atmosphere into space. Because unfixed hydrogen has a low molecular mass, it can achieve escape velocity more readily, and it leaks into outer space at a greater rate than other gases. The leakage of hydrogen into space contributes to the shifting of Earth's atmosphere and surface from an initially reducing state to its current oxidizing one. Photosynthesis provided a free source of oxygen, but the loss of reducing agents such as hydrogen is thought to have been a necessary precondition for the widespread accumulation of oxygen in the atmosphere. Hence, the ability of hydrogen to escape from the atmosphere may have influenced the nature of life that developed on Earth. In the current oxygen-rich atmosphere, most hydrogen is converted into water before it has an opportunity to escape. Instead, most of the hydrogen loss comes from the destruction of methane in the upper atmosphere. Section 8. Life on Earth. There's an image. Fungi are one of the kingdoms of life on Earth. A planet's life forms inhabit ecosystems, whose total forms the biosphere. The biosphere is divided into a number of biomes, inhabited by broadly similar plants and animals. On land, biomes are separated primarily by differences in latitude, height above sea level, and humidity. Terrestrial biomes lying within the Arctic or Antarctic circles, at high altitudes or in extremely arid areas, are relatively barren of plant and animal life. Species diversity reaches a peak in humid lowlands at equatorial latitudes. Estimates of the number of species on Earth today vary. Most species have not been described. A planet that can sustain life is termed habitable, even if life did not originate there. Earth provides liquid water, an environment where complex organic molecules can assemble and interact, and sufficient energy to sustain metabolism. Plants can take up nutrients from the atmosphere, soils, and water. These nutrients are constantly recycled between different species. The distance of Earth from the Sun, as well as its orbital eccentricity, rate of rotation, axial tilt, geological history, sphere, and magnetic field all contribute to the current climatic conditions at the surface. Extreme weather, such as tropical cyclones, including hurricanes and typhoons, occurs over most of Earth's surface and has a large impact on life in those areas. From 1980 to 2000, these events cause an average of 11,800 human deaths per year. Many places are subject to earthquakes, landslides, tsunamis, volcanic eruptions, tornadoes, blizzards, floods, droughts, wildfires, and other calamities and disasters. Human impact is felt in many areas due to pollution of the air and water, acid rain, loss of vegetation, overgrazing, deforestation, desertification, loss of wildlife, species extinction, soil degradation, soil depletion, and erosion. There is a scientific consensus that humans are causing global warming by releasing greenhouse gases into the atmosphere. This is driving changes such as the melting of glaciers and ice sheets, a global rise in average sea levels, and significant shifts in weather. Section 9. Human Geography. Main articles: Human Geography and World. There's an image. The 7 continents of Earth: North America, Europe, Asia, South America, Africa, Australia, and Antarctica. Earth's human population passed 7 billion in the early 2010s, and is projected to peak at around 10 billion in the second half of the 21st century. Most of the growth is expected to take place in sub-Saharan Africa. Human population density varies widely around the world, but a majority live in Asia. By 2050, 6 to 8% of the world's population is expected to be living in urban rather than rural areas. 6 to 8% of the landmass of the world is in the northern hemisphere. Partly due to the predominance of landmass, 90% of humans live in the northern hemisphere. It is estimated that 1/8 of Earth's surface is suitable for humans to live on. 3/4 of Earth's surface is covered by oceans, leaving 1/4 as land. Half of that land area is desert, 14%, high mountains, 27%, or other unsuitable terrains. States claim the planet's entire land surface, except for parts of Antarctica and a few other unclaimed areas. Earth has never had a planet-wide government, but the United Nations is the leading worldwide intergovernmental organization. The first human to orbit Earth was Yuri Gagarin on the 12th of April 1961. In total, about 550 people have visited outer space and reached orbit as of November 2018, and of these, 12 have walked on the moon. Normally, the only humans in space are those on the International Space Station. The station's crew, made up of 6 people, is usually replaced every 6 months. The farthest that humans have travelled from Earth is 400,171 kilometres, 248,655 miles, achieved during the Apollo 13 mission in 1970. Section 9.1 Natural Resources and Land Use. Main articles: Natural Resource and Land Use. There's a table: Land Use in 2015 as a percentage of ice-free land surface. Earth has resources that have been exploited by humans. Those termed non-renewable resources, such as fossil fuels, only renew over geological timescales. Large deposits of fossil fuels are obtained from Earth's crust, consisting of coal, petroleum, and natural gas. These deposits are used by humans both for energy production and as feedstock for chemical production. Mineral ore bodies have also been formed within the crust through a process of orogenesis, resulting from actions of magmatism, erosion, and plate tectonics. These metals and other elements are extracted by mining, a process which often brings environmental and health damage. Earth's biosphere produces many useful biological products for humans, including food, wood, pharmaceuticals, oxygen, and the recycling of organic waste. The land-based ecosystem depends upon topsoil and fresh water, and the oceanic ecosystem depends on dissolved nutrients washed down from the land. In 2019, 39 million square kilometres, 15 million square miles, of Earth's land surface consisted of forest and woodlands. 12 million square kilometres, 4.6 million square miles, was shrub and grassland. 40 million square kilometres, 15 million square miles, were used for animal feed production and grazing, and 11 million square kilometres, 4.2 million square miles, were cultivated as croplands. Of the 12 to 14% of ice-free land that is used for croplands, 2% was irrigated in 2015. Humans use building materials to construct shelters. Section 10. Cultural and Historical Viewpoint. Main article: Earth in Culture. There's an image: Earthrise, taken in 1968 by William Anders, on board Apollo 8. Human cultures have developed many views of the planet. The standard astronomical symbol of Earth consists of a cross circumscribed by a circle, representing the 4 corners of the world. Earth is sometimes personified as a deity. In many cultures, it is a mother goddess that is also the primary fertility deity. Creation myths in many religions involve the creation of Earth by a supernatural deity or deities. The Gaia principle, developed mid-20th century, compared Earth's environments and life as a single self-regulating organism, leading to broad stabilization of the conditions of habitability. Images of Earth taken from space, particularly during the Apollo program, have been credited with altering the way that people viewed the planet that they lived on, emphasizing its beauty, uniqueness, and apparent fragility. Scientific investigation has resulted in several culturally transformative shifts in people's view of the planet. Initial belief in a flat Earth was gradually displaced in ancient Greece by the idea of a spherical Earth, which was attributed to both the philosophers Pythagoras and Parmenides. Earth was generally believed to be the centre of the universe until the 16th century, when scientists first concluded that it was a moving object, comparable to the other planets in the solar system. It was only during the 19th century that geologists realised Earth's age was at least many millions of years. Lord Kelvin used thermodynamics to estimate the age of Earth to be between 20 million and 400 million years old in 1864, sparking a vigorous debate on the subject. It was only when radioactivity and radioactive dating were discovered in the late 19th and early 20th centuries that a reliable mechanism for determining Earth's age was established, proving the planet to be billions of years old. This sound file and all text in the article are licensed under the Creative Commons Attribution Share-alike 3.0 unported license, available at creativecommons.org/licenses/by-sa/3.0.